It's normal for vascularity to be regular. Do you understand me? It means that the contrast agent doesn't stay in any person or anything that comes out of the kidney. So there must be a washing out from the tissue through its blood flow. The circulation continues normally. So when it exits the tissue, will the signal intensity increase or decrease? It will increase. Why will it increase? The effect of the contrast agent was that it reduced T2, and when it moved, T2 returned to increase its duration. So my MX1 started to grow, and it became larger here. All right, Dafar. This form, which is the dynamic scan contrast, involves taking perfusion, allowing you to see the plot flow or observe the contrast agent moving through the tissues. They always use a sequence called echoplanar imaging or echoplanar sequence in this context, which is considered an ingredient sequence in this subject. It remains a very quick examination that takes multiple echoes and observes the flow of the contrast agent within the organ or tissue you want to study. For example, this curve shows that I am taking a lesion, and you can also study it at the level of the region of interest. Here, for instance, you want to see how the flow is in this area. There might be a flow plot in one area that differs from another area, so you can observe the differences. Sometimes they also study cases like this. Look here. For example, there was a change in the signal in these places. I want to show you, in the breast, for instance, if we assume that I am not talking about T2, but rather about T1, how would it look? If we flip the situation to bright, yes, it would be bright. So would the curve go up or down? God bless you. So now, why is it high? Because at this time, the decrease in T1 means that the MZ is high, which means that the signal is more bright. That's why the signal is more bright for the signal we benefit from T1. Now let's talk about the last thing, which is the most difficult. So, what's the topic of spectroscopy? I was just talking a little while ago and mentioned that all the atoms I have give me precision frequency. I can say that all the atoms in the world, guys, contain protons. The proton is present in the nucleus, and this nucleus exists in every atom in the world. So, any compound or any atom you can imagine in the world must contain some protons. It must have a proton, okay? What does this mean? It means that I can excite any proton in any substance. So I can receive a frequency or signal from a proton present in creatinine, for example, or in choline. These substances I keep mentioning are important as they provide indications about my pathology inside the body. For instance, if I have a tumor, this tumor is a result of a certain pathology or specific problem. This problem increases the concentration of some metabolites and decreases the concentration of others. If I can determine the concentration of the metabolites present in my pathology, it will give me an indication of the type of problem. And if I am following up with you and the situation has gotten worse or something like that, then knowing about your internal condition is very important. So how do I do that? You said you want to take my information not just about the tumor or your internal condition, which is very important. So how do I do that? I want to obtain my signal from the metabolites, not just from water. The most significant signal I have is from water. So when we look at the shape, the signal coming to me from signal intensity is this signal intensity on the y-axis. And here what they call parts per million, which is the chemical shift that I will talk about in a moment. The shape of the signal that I always rely on in my image looks like this. This is the signal for fat, and this is the signal for water. So which one has a higher signal intensity, fat or water? The signal intensity of water is higher than that of fat. Great, but there is a difference between the two. What does that mean? The difference is what I call the chemical shift that we talked about earlier. So this difference is called the chemical shift. The difference is between the frequency of water and the frequency of fat, the hydrogen present in water and the hydrogen present in fat. Now, the metabolites that are present in my pathology are all located in this area. Here is the water, and here is the fat. Are their signals weak or strong? Okay, I want to take any signal. How do I take the signal of these metabolites and analyze it to produce a spectrum? You need to eliminate the water signal. How do you know the frequency of the protons in water? You find out at what frequency it resonates and give it an RF pulse before you start the MRI spectroscopy. What do you do when I give it an RF pulse? Remember the saturation topic I was talking about. I was saying that I can apply a saturation pulse to eliminate the hydrogen present in water. In this case, I can start the MRI spectroscopy sequence, focusing now on the metabolites. This is very important. I will get a spectrum that looks like this. This spectrum always has a distinctive shape. The tumor or neurons contain a substance called N-acetylaspartate, and its curve is usually very large. In normal conditions, it has a curve like this. N-acetylaspartate is the highest peak present. This is the normal shape. The concentration of N-acetylaspartate, creatine, and choline, these three metabolites, give me a clear indication of my pathology, where its status is, what type it is, and what its condition is. I have already removed the water that was covering these signals, so I find that the N-acetylaspartate has a very high peak, the highest one, while creatine and choline are next to each other. Now there is a difference in frequency between N-acetylaspartate and creatine and choline. I call this difference parts per million. The parts per million indicates how much difference there is between the frequency of N-acetylaspartate and creatine, meaning you have a difference like this. It doesn't mean the frequency value itself, for example. For example, here I have the fat and the lipids or water, and my lipids have a difference between them of about 220 Hz in frequency. The lipids or fat rotate faster than water, with a difference of 220 Hz. I call this chemical shift 3.5 parts per million. What does that mean? It means on this scale, the frequency of the lipids here is, for example, 1.5, and the high scale is 5. So the difference between 1.5 and 5 is 3.5 parts per million. This is the difference between the peak of the lipids and water. This difference of 3.5 parts per million, when multiplied by 64 megahertz, what is 64 megahertz? It means I have a 1.5 Tesla device that makes the protons rotate at a speed of 64 million hertz. So when I multiply I just have the difference I mentioned between the interstitial fluid and water is 3.5 parts per million. This is because the peak for the interstitial fluid is 1.5 and the peak for water is approximately 5. So the difference between the two is 3.5. When I multiply these by the frequency, when I multiply them by a frequency value of 64 megahertz, which is related to my device of 1.5 Tesla, the resonance frequency gives me a frequency of 20 Hz. So this is the meaning of the term 3.5 parts per million. The same applies. As I said, I want to eliminate water suppression. Once I remove the water, I will have the NAS, creatinine, and choline, which are the substances I am working on. Now, you have, for example, the NAS sportate, which is the big peak I am talking about. Where is this first one found? It is found in the neurons. If there is a tumor or a specific disease, this tumor causes a loss of neurons. So, do you expect that when there is a loss of neurons in the nerve cells, the concentration of NAS will decrease or increase? It will decrease, right? In certain cases of hypoxia, or when there is a neurodegenerative disease, or a tumor, or any issue affecting the neurons, we certainly observe that we will find that the curve, instead of being large like this, starts to decrease. This indicates that there is a significant and noticeable problem or a specific pathology in this patient. Now, let's take creatinine as an example. The same idea applies. For example, if you have a high grade of astrocytomas, for instance, it starts to show in its signal. Creatinine is also a distinctive and reliable marker. Normally, its peak is very close to that of choline, with both being quite similar. And this is the characteristic style of the spectrum we observe. This gives you an indication of a specific issue, and these give you indications of other things. Each one of them, or the peak itself, shows how it looks. This indicates that there is a problem in the tissue, so the concentration relies on how the peak or signal intensity looks. When the concentration decreases, the signal intensity decreases. When the concentration increases, the signal intensity increases. Okay, now let's get to the hardest part. I have something called single voxel spectroscopy and multivoxel spectroscopy. What does this mean? It means that when you come to perform spectroscopy, you select your region of interest, like in the case of this meningioma, for example. Then you create a square and tell it to perform the spectral analysis in that square. How does this curve come out? Here is the bottle and here is the clinic. You can see the shape of the curve changes, right? So the question here is, how does this curve come out? And why doesn't it give me the signal from the entire brain? I mean, why do I choose how I can specify a certain voxel and tell it I want the spectral analysis for this area only? I can also choose another voxel in a normal location and say this is its spectrum, like here, for example. Look, guys, yes. How my device transmits a voxel, it selects this voxel. Let me explain to you, for example, with a lot of subscriptions to the channel, first, am I dealing with pixels or voxels? I currently have this brain, and there is a tumor, and I want to measure the metabolites present in this area. Am I treating this image as 2D or 3D? Am I dealing with it in the X plane only, or in the XY? And Z planes? I still have to treat these pixels as if they are voxels in the X, Y, and Z dimensions. This is the Y, this is the X, and this is the Z. All right, what do I want to do? I want to tell the machine, I want you to extract the signal from this square. At the same time, I want to say, cancel the signals from the other tissues. I don't need them. I only want this voxel. Is that correct? Because if I take the signal from the entire brain, there will be interference. I only want to focus on this voxel. How can I make the brain
Or how can I make my device understand that it should only excite this voxel and receive the signal only from this voxel? This is the trick. How do I do this? Now let's focus together, everyone. Here is the brain, and here is the voxel that I want to work on. If my voxel has dimensions x, y, and z, there are other voxels and pixels next to it that I don't want. I don't want to create them. Do you remember my sequence? I used to give a 90-degree pulse. And with the 90-degree pulse, the slice selection gradient had a specific function. What was the function of the slice selection gradient? The excitation for the slice, which I hope you can help me with, doctor, means that right now I'm not giving the RF. I just want this slice. So, is this slice that I'm going to take here, does it have my voxel or not? Great. Then they tell you, after you do this, you should apply another gradient with another pulse of 180 degrees. Didn't we work, for example, with spin echo giving 90 and then giving 180, and then you receive your signal? So they told you with the 180, apply another gradient but in the y direction. It's like this is in the x and this is in the y, as if you did slice selection but in the y direction. So, in this case, how will my slice look? It will look like this. Imagine you are working with axial, coronal, and sagittal views. You want to take the voxel in all three views. In the first axial, you did it, and in the second, you will take it as if you are taking it in the y-axis. So, you will proceed like this. And what happened is that this image here shows you better. Its clarity is better than its clarity. This is the first segment. I will make another one. Can you see where it is on the axis? I have three gradients, x, y, and z. Please respond so I can feel that I am not alone. Now, I have three gradients, x, y, and z, right? Okay, this is the RF pulse on the axis. It will give me just that. I want to do, doctor, between the three to just get this one out. Is that perhaps maybe acceptable? Here it is again. What do I want to do? Here is RF plus what? Okay, do this for the entire segment. And here is RF plus O. Yes, yes. The point is the point that was presented, which is between the three. Yes, this point is the point that made the 180 not taken because the segment, because I applied the 180 in this direction or in a different plane. Therefore, this part was presented, guys. It was not presented. This part did not take 180. So when I give another plane in this direction, what is the point of overlap between my three planes? This point is the voxel you chose, and this voxel is the one you excited. This is what will give you the signal you want. But what happens to the others? The others? Well, once you apply the 90-degree pulse and the 180-degree pulse, all the protons in the remaining slices will undergo relaxation. You won't get any signal from them at all. You need to apply 180 to rephase and collect the protons again to give you a signal. So now you are focused on where your signal came from, all from one single box. Yes, that's a lot. The difference is that a pixel works with the image as if it is two-dimensional. Is your mobile phone image two-dimensional or three-dimensional? Beautiful. So what does three-dimensional mean? It means you can see it from all angles, from the X and Y. You are two-dimensional, meaning X and Y. So, if you add depth, like a 3D image of a city, you see it in 3 dimensions in X, Y, and Z. You see the image's length, width, and depth. When I talk about it in 2D, I see it in X and Y, but if I want to see its third dimension, I call it a voxel, right? Of course, you want to see the concentration of N-style aspartate, choline, and creatinine within your tissue, within your tumor, within the lesion you are seeing, so it gives you a spectrum. This spectrum that I presented to you a little while ago I need a 90-degree pulse and a gradient in the X direction, then a 180-degree pulse with a gradient in the Y direction and a gradient in the Z direction. These 3 gradients come together, and then I record the signal. The signal I receive is in the form of spectrum analysis. I have 2 things. One is called single voxel spectroscopy, and the other is called multivoxel spectroscopy. In multivoxel, you perform multivoxel. Instead of working on a single voxel, you work on several voxels. How? By applying another gradient. I did this once, and they told me to repeat the sequence, applying a gradient here, a gradient there, and a new gradient. Each time, you take the voxel next to it, as if you are changing the location of the voxel. This is called multivoxel spectroscopy. This technique, which is called point result spectroscopy, is the pulse. The clinical applications related to epilepsy, ischemia, neurodegenerative diseases, psychiatric diseases, and inborn errors of metabolism are important. Look here, for example, at 2 pixels or 2 voxels. This is the normal shape, and this is the shape with a tumor. What is the difference in the 2 pixels? Here, the N-style aspartate is high, and here the concentration of choline is low, while here the concentration is high. This gives you an indication that there is cancer, which is an increase in choline and a decrease in creatinine. Of course, I am not a doctor, so I will understand it better than I do in this matter. But if there was a doctor with us, or someone who has experience in MRI spectroscopy, it would be better at explaining or managing these things. Well, has anyone actually taken the time to ask about this matter? It's important to consider whether anyone has genuinely inquired or shown interest. Has anyone really asked the necessary questions to understand the situation fully? We must ask ourselves if the right questions have been posed to get to the heart of the issue. Has anyone asked? The specific absorption rate, what does it mean? For example, now regarding the fetus, the amplitude, right? From my experience, this is used normally, not to the extent that it will affect him, but how many Teslas do I have? It's not 1.5. It is used normally, meaning it won't have that much of an impact. The effect is, I have a few Tesla, not at 1. 1, 2. Please take these effects into consideration. Yes, of course, the topic, folks, is considered among those we talk about. If you are talking about high machines, 3 Tesla, 4 Tesla, this can happen. Or even at 3 Tesla, it can happen. For example, if the conditions are wrong. The body itself is in contact with the coil. There is no padding. The body is touching the magnet. This can happen because the coil's wire is wrapped in a certain way. So, it might be stable, but we are talking about standard conditions. Under normal circumstances, no, of course, everything is very safe. All right, everyone. Sorry, the lecture is a bit heavy, but thank God, the Lord of the worlds. I am Dr. Emmanuel, and Dr. Mohammed might be a bit lost from us. For a while. No, God willing. Look, doctor, just watch the video. It's all good. The topic is being followed, just like Dr. Hilo and Dr. Dua, for example. They will definitely be a bit more in tune and understanding because they have been with us from the beginning. So that's why just take this week to move forward. It's another opinion, and watch all the videos in order. You have time, and if you need anything or if there's any urgency, feel free to reach out to me, Dr. Mohammed, or anyone else among you. Don't hesitate to contact me, and I will be with you, God willing. If you have any questions or if there are any doctors, God willing, Ramadan Mubarak to you all. Ramadan Mubarak to you. Peace be upon you.